Were you able to connect? Yeah, cool. So if you go to the 9th week, you can find this lesson over here. So today we are going to learn about how to build up a speech to text model, right? So in the past lectures, we have learned about how to build up a face recognition model using embeddings. And we also know how we can make sure to build up a face recognition model using deep learning, right? Taking an image, creating convolution networks, finding out the features, and the faces will be recognized based on that. But in practical way, if you want to make a face recognition based attendance system, that is not feasible because every time the new person joins, we have to do the training again. We have to do these all the thing from the beginning. So that is not feasible. So therefore, we went with the face embeddings model, right? So where it identifies certain features and match with the features when you take a photo and say, okay, this is matching with Logi's embeddings 70%, 75%, something like that, right? So that way we have built up the face recognition system. Then when it's come to emotion recognition system, we realized the emotion of each person remains more or less the same. So I can say anyone is happy or not by looking at the face, right? So regardless of the face, the emotion remains the same. So in that case, we can go for deep learning based system. So that means the way the person looks happy or sad, I can look at the face and let him know it doesn't matter whether he's a Chinese or a Japanese or an American or a Sri Lankan. When they're happy, they smile and we can recognize he's happy. So that's why we went for deep learning model because it's a common emotion, common thing. So once we define that, after that we can apply for most of the things. So again, we discuss about the bias in the data. So if you want to build up a model for emotion recognition in Chinese, it's always better to use this Chinese face expression model. For Japanese face expression model. So we collect Japanese photos with happy faces, sad faces, angry faces, then we train the model. Then that is more suitable for Japanese. But if you ask me, will it not work in Sri Lankan faces? It will work. But the accuracy might be low because their facial features and the expression features extracted by the convolution layer may be different from that is going to extract from us. So that's how the emotion recognition went. Then we came into the voice recognition. You missed that lectures last week. So we did two ways of voice recognition. For example, if you want to, you might have seen in audio like English movies, voice-based door opening systems, right? So they have multiple security options. One is fingerprint, face recognition, and voice. So once all these clarified, only the door will be unlocked for bank applications, many security places when you want to go in, right? So in that case of application, again, if you want to put a voice-based unlocking system, it is not feasible. Okay, when a new person come, you collect thousands of voice clips of him, do the training. It's not feasible actually, right? So again, what we have done is there is a model we used during the last lectures to identify certain features from my voice. So that is my voice tone, frequency, my spectrum of that voice, or multiple features will be extracted from my voice according to the same as the facial features is extracted using the OpenCV. We used another library to extract the voice features and it put it in a matrix. Okay, these are the features. So 256 features are extracted from my voice and put it into an embedding, right? So when I talk back again, it will go back and search those embedding and say, okay, this voice 70% matches with Logi's embeddings. So this might be Logi. So that is the easiest way to build up similar to the face recognition system, right? That we have done. But that is not more accurate because the voice can change very simply, right? Maybe if you get a cold, your voice changes very quickly, right? And maybe if you wear a mask or based on the room that you talk, everything depends on the changes in the voice. So therefore, the voice embedding based system is not highest security enough to put for a security system, right? So, and another thing is anybody can come and mimic, right? Like me. So there are mimicry artists. So that is not a better way. So to avoid those things, we have to find another alternative way, that is deep learning based. So when it's come to the deep learning, how we are going to put the voice inside the deep learning model? Because we know convolution matrix, how it performs to do the feature extraction. So we gave an image, that's fine because it go through the image pixels, identify the feature and extract the features. How we are going to do with the voice? Voice is time versus vibration or time versus magnitude, 2D, time, magnitude. So how we are going to get the matrix out of, right? The matrix is needed to put into the convolution layer. So we came up with something called spectrogram. Have you watched this video last week? Okay. So I'll walk you through that today also. The spectrogram is something like this. Like this. So from your voice, we create kind of a 2D map, right? Where we have a time, we have a frequency, and we have the magnitude as well, using the colors. The color is the magnitude. So this is the frequency. In this frequency, the magnitude is high. So this is the highest magnitude. Lowest means dark color. Sorry, yeah. Yeah, lowest means dark color in decibel. Light means highest magnitude. So now we have a kind of a picture. So this can be put into the convolution matrix to identify the voice features. So that's how we created the voice features during the last lectures. We also have performed perform the convolution based deep learning model training, then we have tested it, right? So that is more feasible for security application because let's say in a place a bank manager might need to log in and a couple of other people might need to log into that system. More than putting the voice embeddings, you create this kind of match and you do the training and put it as a model. So if you want to change the model, you have to do that training again, right? But it's highest security compared to the voice embedding, right? So why the voice embeddings is not secure? Because there are many things that I can come up with. One is voice can change easily. Second thing is anybody can mimic the voices. As I speak, somebody can listen and they can mimic my voice. Another thing is these features are not consistent. So we extract 256 features, but we don't know what are those features that they are doing. So we can extract more features out of a waveform, but still it's not secure enough. So now, after that, we came into the speech to text. Speech to text. So now we know how to recognize the voice based on the person because that image is going to be different for each person, right? The frequency of my tone, bass voice, my bass, my frequency, my high frequency, and loudness, everything are certain features, right? So based on that, I created that 2D map, like an image, which is time versus frequency and the magnitude. Then I put it as a feature input. Then I train the model. So when I speak, first immediately that feature will be constructed based on the mathematical model. That will go into the convolution network, tune neural network. Then it matches with the output and say, okay, this is low, right? Or match is not found. So something like that. So today we are coming to do that speech to text model. So it's not a new model at all because this have been there for a long time. Since 2001, Google is using speech to text. But the issue is how accurate it is. So now we need to make sure what we talk in natural language, the machine should understand what we are talking, right? So when you teach a kid, how you do that? Do you talk for one word one time and you expect the kid to remember that all time? So when the kid learns, it's always trying to listen to the words many people talk and it try to understand what we are talking word by word, right? So for example, if a kid is asking, do you want this? If I say yes, yeah, yes means it's try to understand, okay, yes. Then later on, many people say yes, then it's understand yes in different voices. So for example, the way I say yes, where the American person is going to say yes, may be slightly different. At the beginning, it might be little hard to understand the slang. For example, when I went to US from here, the first semester was a disaster for me because it's very hard to understand their slang. The accent is completely different than ours because our one is, we call it British accent, but it's not. It's typically Sri Lankan Asian accent, right? Yeah. So even when you hear to the British accent, it's even more hard to understand because they are very fast. And person to person, the accent is different. So how we make sure the machine understand what we talk? You talk, it's understand. I talk, it's understand. How we make sure? That means we have to tell the machine different type of yeses, right? We have to collect the yes tone and we have to tell, okay, these are yeses, these are no, this is left, this is right, of different voice, different tone, different slang from different region, right? If you talk to a Philippine guy, his yes will be completely different. Chinese, even you will not understand whether he is saying yes or no. So that kind of accent is there. So then how we make sure the machine understand, right? The same process that the human go through. If you talk with the Chinese for a couple of minutes, then you will understand, okay, he is saying yes or no or left, right? You will understand his slang, right? Maybe Philippines, it's little harder. I work with Philippines. It's very hard to understand the English slang, right? Similar to that, the machine also will find it harder. So when you take the speech to text model, where it have been used? If you go to your AI chatbot, right? There is a teaching assistant in your platform. There is a mic option. When you talk, it listen and it's type, right? It is speech to text. But if you see certain words you say, it won't catch up. Why? Your accent is completely different, right? Than the model that we have using there. It's an open source available model which is trained for maybe the English accents. So when you talk something, it might catch it little different because of your accent. So how we can avoid it? Collecting Sri Lankan accents, many people voices, and training the model will overcome that issue, right? For Chinese, it might face it harder because Chinese accent is completely different than ours, right? In English accent. So when the Chinese talk English, the model that we have embedded into this chatbot for the speech to text will not work. Or it will not understand and it will not convey what the human is saying. So the better way, we have to collect data and we have to retrain to do the thing. So that's what we are going to do today. So one is that one. Another thing, you take your phone, hey Siri, set the time alarm for 5 a.m. or 6 a.m., right? So I have a Google Mini in home. So in Sri Lanka, that Google Home app is not allowed officially to be installed. So I'm just using that to turn on, set up an alarm and wake me up in the morning. So I just say, hey Google, wake me at 6 a.m. That's all. Then it just understands. So that is understanding my natural language. So therefore, it's called natural language processing, NLP, right? If you hear something called NLP, that is this one, natural language processing, right? We are going to process the natural language. So this is English, but it doesn't matter which language you are going to process. So the same training that you have to build for singular language processing, you detect the singular language while talking and convert it, then do it, right? So certain places, they do the singular language processing in dialogue. So all these call center calls are monitored, even Mobitel, converted into a text, right? Then they analyze how the uh, call center agent performed or acted nicely or harshly to the audience, and they rate the person. So like that. But what they do is they convert what I say into an English chat, and now you can convert that English chat into a singular. When you type in English, you can convert it into a singular language, right? So that's how they do it, right? But it's not much efficient, right? But if you train a singular language NLP model, which can understand singular language while you talk, then it can perform better than what they have do now. They type it in English, put it into the singular text typing, get that singular thing, and they do that analysis, right? So translate it in English, put it back into the GPT or something, and get the analysis back and do the translation again into single. So it's a huge process, but due to this translation and everything, certain information misses, right? So we have to use a different technique. If we have a model for single NLP, that will work, right? So now we are going to learn Sinhala or Tamil, whatever the language that we are going to use, we are going to do. So Siri, Google Home, and many other chatbots, whatever the things you name it, they are using this voice to text model. So speech to text model, right? So if you see, it's not started recently. This research started 1950, right? Even if you see how the machines, like when is the AI started? 1956, initiated 1956. So after the World War, if you ask me when the innovation happens a lot during the World War time, 1 and 2, many invention happened during that time, right? Including what we call it as IT, communication, everything initiated during that time due to the World War, to communicate with the army, to safeguard the army and everything. So that's why there are two engineerings at that time. One is called civil engineering, which serves the purpose of the civilians, and the second engineering called military engineering, which serves the purpose for military. Then the civil remains the same, civil engineering. Military break into mechanical, electrical, electronics, computer science and everything are the part of the military engineering. If you take a computer engineering degree, there is electrical engineering courses, there is electronic communication engineering courses, and also computer major, right? If you take electrical, we have other courses as well. Why? Because it came from the same mother called military engineering, right? So during 1950s is a very important thing. After the World War and British left many other places to their place, then the innovation started. Then the humans started thinking, okay, we have machineries, we are doing a lot of work over there with the machines, but still the machine doesn't like thinking like a human. So it's not performing like a human. So how we can make a machine work like a human? That's how these AI initiate, right? So before that, during that 1950s, around 56, 50s to 60s, the first speech to text model was implemented. When you tell a number digit, it was able to identify. But it's a completely different technique that we are going to use now. It's not a deep learning, it's not a neural network, it's a different technique, right? So maybe you talk, it's plot, and based on that, there's a signature. When you tell a word, on the tape recorder, it put a signature. Based on that signature, they analyze the signature back and they might came up with a digit number, right? Similar to that we are going to do in a different way. But earlier days, there is no much computers available. Computers not at all there, I would say, with the GPU or CPU high power. So it's a very basic waveform based pattern. So you talk based on the 1, 2, 3, there are different pattern forms. So based on the pattern, you can say if this pattern is this is 1. This pattern is this is 2, right? So like that. So how many of you have seen the tape recorders, right? Yeah, definitely. So tape recorders, you put it in the cassette and you turn, record and play. Then when you talk, it will record. Basically, it's going to throw a pattern on that tape. So when you play back, that pattern is going to be go through that thing and it reads and play back. So that means for voice, for a certain word, a certain pattern is there. So that's what they have used in 1950s. Then after 10 years, IBM introduced its first capable to identify multiple words together. For example, 5 plus, 3 plus, 8 plus, 4 minus 9. Give me the total. Then it will say 70. So that means it's understand multiple string of words. Still based on the numbers. In 1970s, they were tried to do that same way based on the patterns of the words, magnetic pattern of the words, or vibration. I would say it's a vibration, right? So they trained this DARPA 1011 words. So that's a huge success during this time, 1970s. 1011 words, right? Including numbers and certain English words much used. And 1980s, so Markov model, it's a mathematical model, was applied to this model and they have enhanced the speech recognition a little bit. In 2001, first Google started the voice-based search in Google. So that was not that accurate during the 2001 time because the deep learning was not there at that time. So they were using simple machine learning Markov-based models for that thing, right? Then 2011, Apple launched Siri came. They started using these features, right? Whatever now you name it, the same way that they have done the training, right? Using deep learning neural networks, right? So the same way we are going to do it today. So now let me know, if you want to use the deep learning, what do you need? The data, the word data, because we are going to make a model which understand what we speak. If I say yes, it should type it as yes. If I say no, it should type it as no. If I say, hey, good morning, I am Logi, I would like to, for example, let me go to that thing and I will show you in real time. Need to be more. So here we go. So this guy, right? So I'm going to go here. Okay, blah, 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 blah. Okay, start check. Okay, here you can see this part, right? So you can go here and click it and allow. Hi there. I would like to know what is meant by optimization function. See how it's typing what I'm saying, right? So now I'm going to say a single word now. Are you going? Are you going? So what is typing? You go one. Why? Because it's not have heard that word called are you go. Let's say in Tamil, vanakkam. Vanakkam. Delete it, back we'll start it again, okay? Yeah, because it's definitely it cannot assist what I talked about. Right. Hi there. Vanakkam. It's typed vanakkam, right? This is the way now the dialogue is doing. It get the word to type, but based on the English thing and converting it to a singular typed version, and they are doing the analysis. But when you say this thing, like singular words, some other words maybe, yeah, Suba Alut Aurudu Dakwe. See, it's typing, but only the English letters, right? So like that. So whatever it has seen, it's typing. So this is actually speech to text. I'm speaking and it's converting into the text. And text to speech means this one. So I go here. This is called so this is called speech to text, right? Sorry, text to speech. Text to speech. So text to speech is the next lesson, right? Today we are going to learn about speech to text, right? So now we need the words which need to be collected by many people. The same word. If I want to say yes, 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 yes from every one of you and 1,200, 3,000 yeses, and then I label it as yes. Left means left, 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 left. Label it as left. So there was a earlier in our uni, there is a wheelchair. So we did a training NLP. So the single NLP training for wheelchair. So it has very few commands. Turn left, turn right, go straight, go back, stop, right? So something like that. Very things in single and recorded lot of voices from singular. Then we did the training. Only that wheelchair will be able to understand that language. Only that words. If I tell anything, it won't understand, right? So if I say left, then it'll understand left, and the left given an operation over there in the wheelchair, then it embedded into that wheelchair motor and it will turn left. So like that. So there are many places. That is NLP, right? But now the thing is, we have generative AI, the large language models, right? We don't want to train NLP anymore. We talk, it understands because the LLM is a multimodal. So what I have told you earlier, the LLM can do the object detection, LLM can do the Raman entity recognition, LLM can do all the AI tasks, what you name it, because it's multimodal LLMs, right? So MLLMs, so large language model. So now we are moving towards that. But anyway, this is how we have performed the NLP task earlier. So before going into this, we have to know the basic of the sound wave, how the sound wave engineering is performed, right? So after that only we can perform these tasks using these data and building up the neural network and convolution layers. All right. So what is an audio signal? If you take an audio signal, basically I talk, the air molecule vibrates and reaching your ear, right? So then you hear it what I am saying. Exactly the same way. So how the air molecules perform. So when you give a push to the air molecule through my vocal cord, and it travels in the air in this certain way, right? So if you take this dark spot, it's coming here, 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 like that. So it's moving, the magnitude is moving. If you take this very close look, it looks like a sinusoidal wave, right? So this is the magnitude, right? That is called crest. And the wavelength means from one point to another for a single one period. And the other thing is tough is the bottom magnitude. Crest is the top magnitude, positive value. Trough is the lowest value. So we have this thing as amplitude and the wavelength. So these are very basic things. Even in O levels, we learn about this, right? In sinusoid. So we can represent a signal, voice signal, using a sinusoidal waveform, right? So if I tell you any noise or any signal in the world, any signal in the world can be reconstructed using by adding multiple sinusoidal signals. If I say it, will you believe? Any signal in the world can be reconstructed by adding multiple sinusoidal signals. Yes, we can do that, right? So any signal, if you name it, we can take it by adding multiple sinusoidal signal waveform. We can create that signal. For example, I'm going to show, this is I used to teach DSP. So let's understand how the sound. Rest of the things you already know how to build the convolution network and everything. So the same process we are going to follow in this as well. So let's deep dive into a little bit theory. So that'll be interesting also. Not theory, I mean, don't worry. I'm just going to show you these. Let me go to that DSP tutorial. I can pull up. Right, let's play this one, okay? So these are multiple sinusoidal signals. I plotted with different frequencies. See, can you see it here? So the red color have a higher frequency and wait until it's plot. Yeah. The green have the second highest frequency. The orange has the third highest frequency and the blue has the lowest frequency, right? So like that, you can see this is one period for within 0.001 second, only one wave is traveling. So these are multiple sinusoidal waves, right? If I add them together, this is how the resultant signal is going to be, right? So whatever the signal you name it, we can break into multiple sinusoidal signal. And when you add that thing, the resultant waveform can be formed. Right? Any waveform, even when I am talking, you record it, you can break it into small sinusoidal pieces. So that means if this is the waveform of my speech, I can break my speech into my multiple sinusoidal waveform. This sinusoid will have a frequency, different frequency, and different magnitude, maybe. Now here it's all the things are same magnitude, but I can have a different magnitude as well, right? So here it's a different frequency, green color one. Orange is a different frequency, blue is a different frequency, right? So that means this is the wave of my waveform. I can break it into multiple different frequency magnitude sinusoidal waveform means I can convert my voice into a different frequency spectrum. Am I right? Because this is my voice signal in time domain. I can break it into this kind of multiple addition. So each sinusoidal frequency is a signal have a frequency and a magnitude, right? So by adding that, I can form this one. So that means by distracting, so in such a way, if I can find this from here to here, then I can find certain features from my voice. That is what called Fourier transform, right? Fourier transform, which actually from the time, this is a higher frequency signal and this is a lower frequency signal, right? So that means within 1 second, how many oscillations going to happen? That's the frequency, right? If you see 50 hertz, for example, if you take the light over here, that is blinking at 50 hertz, but you cannot see it, right? You cannot see it because your eye is not capable of seeing 50 hertz blinking signal. Why? What is the frame rate for a video movie? If you want to watch a video, do you think it's a continuous signal? No. 30 frames were captured per second. Every second, 30 frames of images were captured. 30 FPS in your camera, it was mentioned. If it's higher definition, it might go to 60 FPS, right? So even 30 FPS, we cannot see its photo. It's look like a real-time movie. So 50 hertz blinking, you cannot see it at all because the human ability is like that, right? So like that, high frequency, low frequency signals are there. So now, let's say, this is the signal that I have shown you, a signal. And now this is a signal, right? And we can classify that signal into two ways. One is called as a digital signal and the other one is called as an analog signal. So this is very important, okay? What do you mean by analog signal? Have you heard this word anywhere? Analog, digital, yes, right? So analog means what I'm talking right now and what you are listening is completely analog. For example, if I plot my voice signal, right, in a time-based signal, let me draw it. I'm talking like this, and my signal is like this. When you record it, let's say, you go there and you take a particular time spot over here. Let's say this is 1 second, maybe 1 millisecond. Then when you go there to 1 millisecond, you will find a part of my voice, right? Then you are breaking into even smaller piece, 1 nanosecond. Nanometer 10 to the power minus 9, very, very small. Then you will still find a piece of my voice. Even if you go into picosecond, femtosecond, 10 to the power minus 8, even 10 to the power minus 100, you name it, you will find a small part of my voice over there. Why? Because this is continuous, right? It is called continuous signal, right? So that's called analog signal. So now the issue is, if you want to process analog signal, it's continuous. If you want to store the analog signal inside a computer with infinite point. So for example, you can break this 1 minute signal into maybe billions points. So if you want to save these billions points into the computer, how much is it possible? It can be. But it's going to take a lot of memory. It's going to load your system. Right? So, but as you cannot see the 58 signal, our ear also cannot differentiate the millisecond delay, right? The millisecond gap, you cannot differentiate, right? So, if you speak faster, still you can hear the words. So, that millisecond gap, you will not be able to process according to the human. For example, what I'm going to do is, rather than plotting this guy as a continuous signal, right? Okay, let's keep this guy as it is. This is the voice of mine, right? This is the voice signal of mine. What I'm going to do now is, I'm going to break this guy into these points, as what we have done for the video recording, 30 FPS, and we play continuously. You see a movie. Similarly, I'm going to break this like this. This gap to this gap time difference is the same. This gap to this gap the time is same. Right? For example, I am sending this guy through a switch. Imagine through a switch. Right? That switch open and close, turn on, turn off, turn on, turn off. So in that case, what I am going to get is, when it's turn on, the signal will be passed. When it's turn off, the signal is not going to be passed. Right? This is the signal that I'm going to get now. Right? Imagine like a switch on and turn off. You are sending this continuous signal, turn off, turn on, turn off, turn on. Then you get these small pieces of the signal. This is called digital. Right? So now we have unlimited data over here, infinite number of data we can break into. Now we have break into finite number of pieces. That is called digital. So when I play this back again in a high speed, you will not be able to understand everything in the line. Right? So that's how the digital signals are taken. So breaking into pieces are called as sampling. 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 So sampling is the way how fast we are going to break it. For example, how fast this switch turn off and turn on. Right? So if you sit slowly, turn on, turn off, turn on, what is going to happen? It's turn on for a 0.1 second, 0.01 second, and it's turn off for 1 second. So what is going to happen? So you have one sample here, turn on, okay. After that, you can have the other sample here. It goes turn off for 1 second. And another sample for here, another sample for here. Like that. So these are the samples you are getting. 1, 2, right? So if I give it to the, if I play it faster, will you be able to understand? No, right? Because this is a signal that I sampled, and due to the low sampling rate, I got this signal output. If I connect this signal, this is the signal output that I'm going to get, right? So that means the sampling rate is an important factor. Sampling means how many pieces, how good you are breaking, how fast you are breaking the signal, right? So that means if you sample it in a low rate, you cannot reconstruct the signal at all, right? So that is called sampling rate. So these are the digital information that we are going to store in the computer. So how many of you play MP3 songs? You listen to MP3 songs, right? Yeah. So is that an analog or digital? It's digital because it's stored in a digital device, right? Computer is a digital device. Your mobile phone is a digital device. So whatever the things, movies, images, whatever you see in your computer, mobile phone, or what devices that you use, all are digital information. But we are seeing it as continuous, right? Let me show you how hard it is to reconstruct the signal. Okay, this is the signal. So I'm going to sample this signal. Okay, this signal has 1000 hertz frequency, 3000 hertz frequency, 5000 hertz frequency, different sinusoidal, and 10,000 hertz frequency. Okay, so that's how I plot it over here, all these 5. So I'm going to sample. That means turn on, turn off, turn on, turn off, turn on, turn off, like that. I'm going to sample this signal at maybe let's say 5 5,000 hertz, 5,000 hertz, right? I'm going to sample this thing into 5,000 hertz. Let's play it, okay? So when I sample it, these are the samples that I am getting. These are the samples I am getting. So it took a sample at this point, yeah, start initial point here, and it took a sample over here, somewhere here, I believe here, somewhere here, and another sample somewhere here, maybe somewhere here, right? Because the sampling rate is low, right? Then I'm going to reconstruct that back again. So how we'll see, we sampled the signal now. This is the original signal that I sampled, right? These are the sampling points that I got after sampling. So when I play this back, it should give this signal, right? But due to the low sampling rate, this will be the reconstructed signal. This is the signal I played, I sampled. When I reconstructed, that means play it in a high speed, right? This is the signal I got. Are these two are the same signal? Completely wrong, right? Completely wrong signal. So sampling is an important thing which determines the reconstruction possible or not. So now what I'm going to do, go here, I'm going to say 100,000 frequency, 100,000 frequency hertz. I'm going to do the sampling now. So that means what is going to happen? See how many samples I got. Very quickly, it's going to turn on, turn off, turn on, turn off, turn off. So that means I'm going to get a lot of points over here, right? Then let's change this to 100,000 and I'm going to play it. Let's see whether we'll be able to reconstruct it. This is the original signal that I sampled. These are the sampling points that I got. Then, yeah, I got the exact same signal reconstructed. So that means sampling is an important effect in an audio, right? Sampling is an important effect in audio. So if you have high sampling rate, you are going to have a good quality signal output, right? If you have a low quality sampling rate, it will be an issue, right? So for example, we can take an audio signal and we can sample it at a low frequency and see how it will be. So if Trump is speaking, hello America, how are you, like that. So if you sample it in a very low frequency, you will hear, that done. That's all, right? Because certain samples are missed, right? At a low frequency. So you have to sample it at high frequency to listen it continuously. So sampling is an important effect. So we call it as sampling rate. So we are going to get these small pieces and store it information as an audio signal. When we get it and play it, we reconstruct and play. That's called digital signal processing. This is different domain. So that is really important when it's come to audio signal processing for us. Okay. Okay. So cool. So now we have learned about this thing. And these are the digital signals. So we break it into points. A continuous signal, we break it into points in order to store it in a digital device. These digital devices cannot store analog data, right? So analog signal is a continuous signal. Even though zoom in, zoom in, zoom in, go to the picosecond, nanosecond, even like 10 to the power minus 100 second, you will find a piece over there in the analog signal. But if I go in the digital signal, you won't find it because you have only certain points over there in the digital signal, right? So that is called digital and analog. So we need digital data to be processed in the computer. So whatever I talk, if I want to record it in the computer or in a digital audio recorder, what is going to happen is it's going to sample my voice and put those points over here as a digital signal. If you take your mobile phone, record it, it's a digitalized audio recorded in your mobile phone. What is happening is it's turn on, turn off, turn on, turn off, turn on, turn off inside, it's called oscillator, and capturing your voice bits. When you play back, it's played in a high speed, natural speed. Then you won't hear it as a breaking option. Okay. So other thing is, then what is continuous device? The tape recorders are continuous. The tape recorders that we have used in the past are continuous. So tell me whether the digital is higher quality data or analog is higher quality data. Definitely analog, right? Because analog have continuous millions of points, right? but digital have certain number of points. So the quality of the digital data is less. But how come the digital MP3 is better than the music that you hear in the analog cassette tape? Because it is processed. Why? Digital data can be processed using computer, right? So the digital signal processing came into action after the computer came into action. Without digital, now it's really, really hard. Digital means the hardware size becomes very smaller, right? So the camera, first invented camera is bigger than this room size. Now we have a camera here, right? All thanks to digital, right? So that is one thing. So as I said, the sampling is one of the concept that we change the analog signal into digital. That is enough for this class, right? So as I told earlier also, this digital signal processing is a 14-week lectures that I do in University of Moratuwa. There are a lot of stuff to do, so we don't want to do it. So now the other question, how you break this graph, if I get this graph, okay, this is my voice graph, let's say, how you break this graph into number of sinusoidal functions. So that technique is called as Fourier transform, right? Fourier transform. So that Fourier transform, when it's applied in the digital signal, so you see, this is a signal, analog signal. I take pieces here and there, and now this is a digital signal. So this is the information that we are going to store it in the computer. So we have a time domain signal, how my voice varies with the time. And when you do this transformation, this signal, time domain signal to the frequency domain, as I said, multiple frequencies extraction, using the Fourier transform, you will get this spectrum. So how many frequencies are in my voice or in the audio signal will be analyzed. So from that signal, blue color signal, I have seen this many signals are there, sinusoidal signal, right? This has a frequency, this has a frequency, this has a frequency, and this has a frequency, different frequencies. So this one signal have this much of frequencies. Then I can plot how many frequencies are there in this plot as a plot that is called as Fourier thing. So here the frequencies and the magnitude of that frequency, right? So that is called, this is time domain signal, this is frequency domain signal. This has certain information with the time domain, my audio signal, and this has the frequency information with the magnitude in the frequency domain signal. But to have the frequency, time domain, and the magnitude feature in one plot, we have generated this one, right? This is called spectrogram or spectrograph, okay? So this is the one we are going to do. So now, spectrogram, some gram, angiogram, there is medical terms to analyze the medical imaging, right? So the baby goes in and the baby is scanned. Certain frequency is sent in and the magnitude is retrieved with the time, and we reconstructed the baby signal, all thanks to this technology, all right? So that is the spectrogram. So now this is the person, this is the image or like kind of information that we are going to give it to the AI model, right? So now it's a matrix. We can break this into a matrix. It has the time features. It has the time features over here. It has the sign features over here. Then it's going to get it the frequencies. What are the frequencies and what is the relevant magnitude? All the three features are here. That's all we need from an audio signal. The same thing that we have performed for the voice recognition, person-based voice recognition during last lecture. So is that clear up to now? Because we are going to start. What is a voice engineering? Like audio engineering is completely based on these three: time domain, frequency domain, and the spectrogram. And for example, I'm talking here in this class. There is a generator working on the another room, which is giving a huge noise, right? Because kind of a noise in the background. So now Para is recording in this audio. He will get that background noise as well, right? Then as an audio engineer, if I was asked to, okay, reduce the background noise. So what I will do is basically, What I will do is basically, give me a second. Yeah. Why it's going up and again? Yeah. So what I will do is, I will take the signal, right? Plot the time domain signal, right? First. Then I extract the frequency information through the Fourier transform. It's a mathematical model. Imagine you send the time domain signal, output is a frequency graph, right? How many frequencies are there in that audio signal and what is my thing, right? So then this is the frequency graph. So then identify what is the frequency of the background noise, right? And I cancel it using a mathematical function, right? Then the noise is cancelled. That's how this audio processing is happening. So pitch matching, auto tuning, all these things are all thanks to this guy. So what they do, the auto tuning, they sing a song, record the audio. Then this is the actual tune where my voice need to be placed. See this frequency, but my voice is over here. What I need to do now? I shift this part to this part. Then the auto tune is done, right? You become as a singer without any issue. So all the things now because of this. See, if you see in the Indian cinema, now the actors have started to sing. Never mind, you sing. We will adjust all these things in this signal, frequency, auto tuning, amplitude, pitch, everything is adjusted using the audio processing signal. Now, singers are not needed for a cinema because actor itself singing the song, and it's become more popular also, right? So that's the thing because thanks to audio digital signal processing techniques, right? So now we will come to our session. Once we need to build up the audio to speech system, what we need to do is basically the data, right? So we do not have enough data to collect yes in the class. So what we will use is, as last class, we will use the data from this point. If you click this one, it will go to a place called time flow diagram here. Then you can see the data. So here the data, if you go to the data, we have a lot of data over here. So which has on, these are the words. Yes, no, up, down, left, right, on, off, stop, go, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And bed, bird, cat, dog. So these are the words that we have recorded from me, from you, like the thousands of people. The yes is told by thousands of people. I record and save it as yes. Right is saved as recorded from different people, different voices and everything. I saved it as no or right. So like that, each and every word I record from multiple people and I keep that as the data. Clear now? Right, that's other data that we are going to have over here. So if you go down, you can download the data. When you want to download the data, so it will want to ask with the Google. So you can sign in with Google. And after that, you can go here. Okay. Account is unverified. Okay, I will verify my account. Okay, never mind. So what you have to do is you have to go here to the Kaggle and you have to go. There are some rules that you have to update, right? So accept. So click late submission and you have to put your phone number. I'm not a robot. Then click send verification code and get the verification done. Okay. I have done it already. If I put my number, it will say no, right? So I don't want to do it. I will use the thing that I have uploaded earlier. So we need a Kaggle file. So just do that verification first. You go here, late submission, go to rules, give this 070597634. I'm not a robot. Send verification code. Too many requests because I have done it earlier. So if you do it, you will get it to your mobile phone. Too many requests? Okay, let me see. Okay. Here there is a button. Just click I understand and accept. And put your mobile number. Okay. How many of you got too many requests? Others okay? Yeah, Glade submission. Go to this link, right? Over here. Yeah, yeah. Then go to the rules, and go down and say, I understand and I accept bound to the condition rules. Accept that one. Then go back to your profile here. Maybe, yeah, Kaggle overview, my home. Go to the home page. Yes, yes. Then go my profile and download your Kaggle API, right? You know how to do it from last week. It's again coming. Okay, it's fine. So do you have the Kaggle file that you have downloaded earlier from the last lecture? Yeah, upload it over here. Then let's install this one. Let's see whether it's getting it or not. Okay. Right. So then play it out. Uh, okay, I'm going to download. Let's see whether it's downloading or not. Else. Okay. No, I need to do that. Okay, then I will download a new Kaggle. Let me go to my original account. Make sure you are in the same account. Huh? This earlier we did not has this issue because those data are open source data, right? So this is openly available, but this data is closed data. So we have to accept their rules in order to do the task. So let's accept and download a new API. I'm going to do that. Okay, I go to rules. I got it. I already have accepted it. So there is no issues. I go to my here settings and go to API, create new token, continue. All right. I downloaded the new token. So I am going to go back to this tutorial again and upload the new token. I will delete this one. Okay. Okay. Then I'll go back here. I'm going to upload the new token, that API that I have downloaded, and I'm going to rename as Kaggle. All right. So now I install the pip. I'm going to make a connection with the Kaggle and let me see whether I will be able to do it. Yes, it started downloading. How many of you have issues? Let me know. I'll come. Kaggle download file. Yeah. Where is the download file? Did you download the file? Yes. Download. What I will do is I will upload my file to that thing. You can go and download it. So that it makes the process easier. The reason is this is a private data. That's the issue. All right, let me upload it to the AI. Under the course, I will add a thing called file. Maybe add a folder, right? I will add a folder. Then you can download it. Okay. Okay. I have uploaded my Kaggle. Can you go and download? It's in a zip folder. Download, unzip it, and load it over here. There's a file you have to load it to this environment. Down the side. Yeah. Drag and drop. Go to the download folder. See. Open it. Yeah. Go to the answer. So you can just close this one. Don't close this one. Yeah. The previous the Google program. Drag and drop this can load you. Yes. No. That file that we have downloaded. That, yeah. where you have to upload? Very good. Yeah, yeah. Here we go. Upload it. Download it, right? Download it. Slower on time. Right? That's it. Emails. And random source. Now, too many accounts handling, it might happen. Multiple people. Yeah, there one account. So what's happening is it's disconnected, connected, so that's have multiple account with the same phone number, it might download. How many of you guys download? Can be, yeah, you just it's not accessible. You download. Oh, download and you unsync also. Yeah, so you have to drag and drop. Yeah. I accepted, that's why I downloaded. Let me check this one. So I'm in my Google account. So once I go here you have to go to the rules and go down, and you have accepted the rules and thing. So you have to go here, and there is under that there is something called accept rules and here. So once it accepted, then you will be able to download. Can you go to that link and go to that rules? Can you click that link? Others, all good, ne? Good. Okay. So this is because of this is a private data that we are downloading. It's uploaded for a competition or something. So that's the reason we have to go through these acceptance and all these rules. Otherwise, open data is very thing. I couldn't find an open data. That's the issue. So let me continue. So once it's done, we have to unzip the folder because it's in the zip folder, downloaded folder. So we have to do the unzipping. So by clicking this unzip the data, you will be able to unzip this folder. So it'll take a while and you will find this another folder called TensorFlow with unzip folder, right? So click that one. So by the meantime, if you could accept that thing, you downloaded my game and uploaded the number. Okay. Yeah, that's good. Yeah. Yeah, download. Yeah, that's because it's in a zip folder. Where is the download? Download folder. No, download folder. In your computer. Can you open it as well? I need to unzip this one. Yeah, downloads. Yeah. And just yeah, unzip and upload also fine. There is another course. That is fine. Yeah, you have to unzip and open. Now it's coming from the zip folder. Now remember. If you unzip and put it in your file. So after downloading, once you unzip the folder, so you'll be able to open up these three things over here. Test 7c, train 7c, sample.7c. It's a folder format. Again, it's a compressed folder. So we have to unzip it. It's not a zip folder, but this .7c is another compressed file format. So we have to unzip that. So we will install this py7zr library need to be installed to unzip these three folders. Right? Zip format is a format. Similar to that, .7c is another compressed file format. So unzip that one, I install this one. After that, I'm going to unzip the train 7c. It will take a while to unzip the folder because there are a lot of files inside it. There are a lot of words that we have seen up, right, left, down, yes, no, like that. Under that, each name, yes, there are thousands of audio, right? No, there are thousands of audio files. So it's a huge process to unzip it. So it will take a while to unzip this folder. So after unzipping the train, unzip the test and unzip the sample submission 7c. That is not needed, but still we will unzip it. So this is why we need to accept the terms and condition because it's a private data. That's the only reason, right? So if is it a publicly available Kaggle data, totally fine. Kaggle is similar to a Google Colab platform, which is started after the deep learning emerging as a data source. For example, they also provide 15 GB of GPU to run your codes and test it out for free version, right? And you can store your data over there, share it with the public. So it's a collaborative environment, really good place. Yeah, GitHub also there. They have a connection internally. Yeah, but I don't know how extent they go for. It will take a while, no worries, because it's a huge file. We are unzipping, and there are a lot of sub files in under that, so it will take a while to unzip those folders. Because the internet is disconnected. and it's refresh. It's okay. Then after that, we have to unzip the 7C, right? I have unzipped it, this one, and I'm going to unzip the test one. So just play it. Yeah. And drag that file and put it on the is happening because the internet is breaking. Yes. While downloading, it got stopped. Let me speak. It only stopped. So once you unzip the test, have you done? Unzip the test? Still going. Go. So sometimes the file not find error might come because of the interruption of this internet. You have to refresh and do that again. So once this 7C is done, it will take a while because there are a lot of other folders inside. So we'll keep it as it is. So once the basic is known, the rest of the things are the same thing as building the convolution network. That's all, right? Rest of the things are the same. So after that, I'm going to unzip this file. Then we are ready to go. All right. Have you unzipped these files? How many of you have unzipped? I'll wait until everyone is doing that. Okay. After that, we have collected the data to the platform. Then we are going to start building up the model. Very, very quick. That is not, should not be there. That's it. Now, you want it? All are seen. 7C. Alright, so now we will move into our real work. So up to now we have collected the data on, right? So now we will build up. So to work with these examples, we need certain libraries. So Librosa is a library in Python similar to OpenCV. OpenCV is for vision programming in Python. Librosa is one thing which is for audio processing in Python. So it has all the FFT, fast Fourier transform, magnitude calculation, spectrum calculation, all these functions are defined. So if you want to calculate the FFT something code, it'll do the whole function. If you want to calculate the spectrogram dot something, it'll do the spectrogram calculation. So we don't want to write the script from the beginning. So we will import the library Librosa and other libraries already you know about it. So we will just build it up. So after that, if you sometimes if you are going to run it in the VS Code, you might need to install this pip install Librosa. Okay, so that's I have added. You have to make sure you have it or not. If you do not have, you have to install it in your VS Code. Okay, so enable this one. For now, Google Colab is already there. So we do not want to install. So we will just load a WAV file. So from the train data set, if you go here, go to train, then go to audio. These are the audios that we have recorded. Bed, bird, cat, dog, down, 854, go, happy house, left, Marvin, 9, no, off. Let's say how many number of audios are there under the off folder. So there will be 1, 2, 3, up to maybe close to 100 files are there. 100 to 100 files are there. Those are, many people have said, no, something. These are the files over there, right? Then they have recorded and put it over here. So let's load one file and see what is that over there. I just already put it over here. So the file path. So you can also copy some random file path, copy as a path and paste it over here. Then you will be able to load it. Right? Let's load it out. So there are a lot of files over here, so that might get stuck. So we will not play with this anymore. We'll just close these folders and we'll go on. Sometimes it gets stuck when you try to open it up. So let's play it. What does this mean? So this is a yes, right? So this is a yes of a person. I load one file and just playing it out. Okay. So now what I'm going to do is, I'm going to plot this one in a time domain way. So if you see, this is the time. She was silent at the beginning. If you listen to that again, right? So no voice. Yes came here. Then after that is sound came. Listen again carefully. Right? So this is the audio signal of that yes. when you plot it as a time domain signal. If you go here, we are directly using this librosa library because it has all the audio processing functions in it. The time domain to frequency domain transformation, time domain frequency domain to spectrogram transformation, everything is there. Just you need to call that library in the domain, librosa. Okay. So just play it out. Then you will get the time domain signal of this one. This is the time domain. So now, let us now look at the sampling rate of the audio signal because the sampling rate is very, very important. Why? If the sampling rating is low, you cannot reconstruct the signal. She will say yes, but you might hear something. That's all. Done. So that is not good. So let's listen the sampling rate of this one. So this signal, actually this signal is sampled at 16,000 hertz. So that means 16 kilohertz, right? 16 kilohertz. That is more than enough because the human voice frequency is around 1000, 800, 750 to 1000. That's the human voice frequency. So if you sample it at 16,000, that is more than enough to get enough points to reconstruct the signal, right? So 16,000 is a good sampling rate. And the issue is now 16,000 means you have a lot of data, right? One yes signal is sampled into 16,000 points. 1 second, 16,000 points we are going to save. That means it's too much for the computer to do the processing. So what we are doing, we are going to increase the computer processing time. So that is not good. I'm going to resample to 8,000. So again, see, librosa resample. That's the code, right? So I just resample the code. Original is 16,000. That's what I determined over here. And I want it at 8,000 because I want to reduce the size of the thing, right? So now let's play it out. Listen this, yes. Okay. After undersampling to 8,000, okay, I'm going to reduce this even to 1,000 to show you how the sampling is going to work. Okay, I'm going to sample it to 1,000. Now play. What did you hear? Nothing, right? So maybe 2,000. Let's see whether we'll be able to, because the points collected are not enough to reconstruct. Now let's see 2,000, how it works. That's all. So 1 point is captured when it's reconstructed completely wrong. 3,000 maybe. See, that's the sampling thing. So you should have enough sampling rate to reconstruct the signal. Let's play. No, because the reason the part is captured and rest is missed, right? So then 5,000. Yes, but the frequency completely different. Why? Because we are basically reconstructing the signal. Sampling is an important. Yes. Again, the voice frequency is a little bit different because while reconstructed, completely based on the points, number of points we are reconstructing. So maybe 7,000. We'll see. Is that enough? Again, the voice frequency is different, but more or less 8,000 gives a similar kind of voice. Okay, here also kind of. So we will keep it to 8,000. It doesn't matter under sampling. So now you got it right. The sampling is a really important point when it's come to reconstruction. So if the sampling is not good, then you are going to get a trashy audio signal. Now, how many of you have listened to music using a low quality Chinese headset or in a Chinese mobile phone? Now you know the reason, right? So they sample it in a very low sampling rate to reduce the processing power of the processor. Finally, what we hear is a completely distorted audio, right? Hearing an Apple phone using an Apple headset and hearing a Chinese phone, even the Apple headset, you will have an issue. The reason, the low sampling rate. Now it's clear, right? So if you are not clearing certain things, it's due to the sampling issue. Increase the sampling rate, then you will get it, right? So now the sampling is 16,000. Do you think you can increase the sampling rate? Original signal that I downloaded is 16,000. Can you increase the sampling rate? No. Why? Because already you have cut the pieces. Right? Right? You already have cut the pieces to 16,000. So from that you can eliminate certain pieces. You cannot construct pieces. Right? So you can go down, not up. Right? Even though you go up, it will be the same signal. Right? Nothing going to change. So we'll use the 8,000 signal for the sampling. Now we will understand what are the voice commands are over here. So now what I'm going to do is, these are the things: background noise, 0, shells, dog, right, happy, 1, down, 3, 8. That means if I take the 8, there are 2,000 audio clips, nearly 2,000 audio clips saying 8, 8, 8. From different people, different voice, male, female, different zones, right? So if you take a bed, there are close to 1,500 audio clips saying bed. Only bed, right? Bed, bed, like that. So like that, we have this many audio signals that we have right now, okay? Then let's see how much audio duration. So even though 1,000, 2,000, 1,500 clips are there for each word that we have collected, so let's see how much duration total together it's coming. Altogether duration. Those are like 1 second, 2 second clip. Yes, less than a second, right? So the total audio duration is kind of 2,000 seconds, right? To 20,000 seconds total audio, right? So that's how. So now we will do the pre-processing. So in the data exploration part earlier, we have seen that the duration of a few recording is less than 1 second and the sampling rate is too high. So let us read the audio waves and use the below pre-processing steps to deal with this. So what we are going to do is we are going to load this audio file first, and we are going to do the resampling to each and every audio to 8,000. And we are going to make the audio to 1 second. If is it less than 1 second, we have to make sure to the 1 second. Now what is going to happen? When I'm talking, if you can go to the chatbot and say, right, tell slowly, hello, I need to know what is optimization function. It will clearly capture, because it's called moving window. Last lectures we have learned. It's going to take a part every second or every 500 millisecond and going to analyze that 500 millisecond and identify the words, right? If I say, I need to know optimization, high speed, it will not be able to, because the window size will not be able to catch the words, right? So we have to have a certain window size. So certain things are less than 1 second. So 0.6 things. So we have to make sure everything comes to 1 second audio, right? So then we are going to redo this thing. We are going to reduce the sample and we are going to increase the width of the things to 1 second. So only we are going to do it for this thing. These are the yes, no, up, down, left, right, on, off, stop, go. So only to this audio we are going to do is, because if you want to do it for everything, it's going to take time. And if you want to do the training for everything, it's going to take time again. So we will only do it for these audio signals. So I'm doing it, everything. Okay, yes, no, up, down, left, right, on, off, go, stop. Now we have processed that audios inside that file. We have resampled it to 8,000. That means undersample all are 16,000, undersampled to 8,000, because we need less number of points to do the training, right? Because it will be more accurate for us. And we have increased the label, right? Convert the output label into integer encoded. What does this mean? So now these are the input. Yes, no, up, down, left, right, on, off, stop. So these are the output that we need actually. Our input is going to be our voice signal. These are the output. Can you input a word as an output in the neural network? No. Even 1 to 9, we have mapped to 0 to 1 to 3. Car, van, object detection, we have put a label. Emotion detection, we have put 0, 1. For angry, 3. Happy, 5, like that, right? So similarly, we have to give a number system for yes, no, up, down thing. So let's give it. So that is, we are giving a integer encoded thing for these labels. So it's going to have 0 as yes, 1 as no, 2, 3, 4, 5, 6, 7, 8, 9 as go, right? So like that. So now convert the integer encoded labels to a one hot vector since it's a multi-classification problem. So I'm going to put it as a vector over here. So the labels are here, categorical thing. So let's put it into a vector format. Yes, no, these things. So that means it's going to say 9 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 by 10 matrix is going to be formed. 1, yes, 0, 0, 0, rest of the things. Second column 0, 1, 0, 0, 0, 0. Third one 0, 0, 1, 0, 0, 0, 0. Like yes, no, up, down, like that. It will be given a matrix value over here. So reshape the 2D array into 3D since the input to with 1D convolutional neural network using the 3D array. So I am converting that into 3D array. How is that? Using this spectrogram technique, right? Now split the train and validation set. We need to do that thing before we going into the training, right? We have a training set. I am going to split that training set into 0.2 for validation set. Rest of the things are going to go for training, right? Cool. Then the model architecture, input is the audio signal, convolution 1D multiplied by 4 times and max pooling. And there is a dense layer that is going to do the classification. Finally, the output is going to be given. The same architecture we are going to build up. So we know these are the important libraries for building up the model. And input shape is going to be 8000 into 1. Makes sense because we have undersampled to 8000. The convolution layer first 813 and we are using the ReLU activation function and max pooling layer 3. So 3 by 3. What is max pooling? Now we have 8000 pixels, right? 8000 by 1 input. So now we have changed it into this one also as a 3D vector now, right? So now this is a big image, big pixel. Now we are going to reduce the size to smaller, right? So that's how we have done for the image also 28. Max pool is reducing the size of the convolution output. So we have 1D convolution, second 1D convolution, third 1D convolution. This is 1D convolution. After that we are flattening. Then the dense layer. Dense layer means our neurons comes in. 256 neurons, 128 neurons. After that, outputs, length, labels. How many labels we have? 10 labels. So 10 output neurons are going to be here. If we add another label over here, okay, I want to add another thing, yes, up, down, bed over here, then it will be 11 output neurons. Obviously. So then after that, we are going to create this convolution neural network by clicking it. The same way we have done it for the character recognition, emotion recognition, everything the same way we have done it, right? The same way we are going to do it. So this is the thing, the summary of the model. So the total parameters that we are going to work with is 161, 1498. So this many parameters we are going to fine tune it now, train it now, right? From our convolution neural network. I just came up with this thing. You can add as much as you want. Okay. You can add a new convolution layer, change the vector size and everything. The accuracy is going to change based on your architecture. This is a random architecture I came up with. Okay. Just run it. After that, what we need to do? We need to define what is the loss function that we are going to use. What are the optimizer function that we are going to use? And what is the accuracy that we are going to measure while we are doing the training. The same procedure as earlier. Model, I have defined the categorical cost entropy is the loss function. What is the loss function? What is the loss function? Forgot? Loss function is the thing, the output. You put the audio, it do the processing, feature extraction, and the classification layer define it as yes. You put it as yes, right? You the audio yes. It do all the things after training. While training, the output determined as no now. Then there should be an error. You calculate the error using the loss function. So that is this categorical cross entropy. This is a different loss function that we are using for this. There are 1000 loss functions. You can change the loss function and you can try it out, right? Optimizer mean what? How we are going to find the optimum value for the weights. So that is the optimizer function. Adam, the same optimizer that we have used for the character recognition also, Adam. Adam is a very common optimizer used in many other applications, right? So because it shows promising optimizing results. And the accuracy metrics, you know what is meant by accuracy. So now we are going to do two things. One is early stopping and the checkpoint. So we are going to save the training model. As I said you earlier multiple times, not the last train model is the best model because you can come down and go up and come down. We don't know where we'll be stopped. So always we check with the previous thing and say, okay, this is this one. So this is accuracy is higher than the previous one, then save the model. Accuracy is less than the previous one, don't save, go to the next iteration. Like that, we save the best model now. Early stopping, I have disabled it here, right? But early stopping, you go home and try it by enabling. Enable means just delete this green color one. That's all, right? You just, I disabled it here. Early stopping means we keep it for higher iteration. So if you are going for higher number of training, we use this early stopping mechanism to stop early until before we reach the number of epochs. Let's say I'm going to define 1,000 number of epochs. So 1,000 number of epochs, sometime what will happen is after certain time of iteration, there will be no much significant improvement in the accuracy. There is no significant improvement in the loss. There is nothing. It's going to come like this and it's going to go like this after a certain time. So if you put 1,000, let's say you come over here up to 50, within 50 iteration, you reach that optimum value. Then after that, there is not much change. You keep the loss function as low as here this is until 1,000 iterations. So then it's waste of GPU time. There is nothing improving. Optimization function reach the optimum value. There is not much improvement. So the early stopping means when we reach to that point, same kind of value is coming again, the accuracy and the value or something, it will stop the train and save it as a best model, right? So if you are using 1,000 number of epochs iteration, early stopping is a way to save the GPU functionality while saving the best model, right? Now I skipped it because we are going to use only 100 iteration, not much, or 30 iteration we will use. And the model fit function, the value accuracy is going to be monitored. So this is the other one. So it compare with the previous iteration and see whether accuracy improved or not. If it improved, save or not, go to the next iteration. So that is called MC. So convert label is to one hot encoding, right? Again done. So now we are going to start the training. Let's run for 100 epochs, right? We are going to run for 100 epochs. Only I am going to call back MC. MC means this one. It's going to check every iteration whether the accuracy improved or not. If you want to add the ES, enable the ES over here and go and type here ES, comma MC. Okay, then it's going to check the early stopping also. So now I'm not going to do that. So now we will start the training. So the batch size is 32. So these are the training parameters I am going to start. So why? No, I did run it, that one. Okay. So now it will be there. So we have started the training now. Let's run it for 100 epochs. What's the issue? Okay, model compile. Okay. Converting to hot encodings, then start the training. What is it happening? All right, let's figure out. Maybe we will run from here. If is it restarted, we have to run from the again. The internet connection is little less, so I'm going to run it again. Yeah, it started. So because it's restarted in the middle when I was talking. So it won't happen if the internet connection is stable. So I tried it multiple times in home. So batch size is 32. So we are taking 533 audio clips, spectrograms for our training, right? So we have reshaped it into 2D. Now the training started. So other thing, why we need the early stopping is to avoid the overfitting. Overfitting means, have you talked about overfitting earlier? So how can I do it? So you start the loss function come like this. After training, it's a flat one. The loss is not changing. So the accuracy goes high. After that, it's a flat one, right? So if you start to the loss function and the loss is not changing much, and you are training again and again and again and again and again, what is going to happen is the overfitting is going to happen. Overfitting means basically, I don't know how many of you believe in God, right? So let's say somebody believe in God. So he go to temple and go to the mountain. He preaches all the thing about God, 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 whatever the things God, right? So then in real life, whatever things happen, they believe that is because of God, right? That is overfitting. So now overfitting happens means the model lose the ability to do the prediction. The ability to the brain, the ability to think scientifically, right? Whatever thing happen is because of God. I'm just saying an example, right? So when you upload a audio and ask what is this, model will lose the ability to do that prediction based on the features. It will say something. So what it thinks as it is, like if is it overfitted on a yes, whatever the things you upload, it will say yes. It doesn't matter, right? So that overfitting is really, really dangerous for an AI training. So we can troubleshoot that overfitting using the loss curve and the accuracy curve, right? So we will see our model gets overfits or not while doing the training. This is still less number of epochs. At the same time, I have constructed the convolution neural network very simple way. We have to have a lot of convolution layers in the before, and we have to do the certain feature engineering. And the number of epochs 100 is not at all enough. And we'll see how our loss function works now, right? After training. Here you can see in this thing, initially I started the best saving to content best model. First iteration, it's saved. Second iteration, it's saved. Third one got saved because it's checking the value accuracy, right? It's validation accuracy. If you take here 0.39, here 0.56, here 0.63, here 0.73, it's saved. 7312 say 7321, right? 7321, here the model saved, right? But when you come to the next, it's 0.7312. Actually, this is less than this, right? Now you can see the model is not saved in this iteration. It says, it's not saved, it said value accuracy did not improve from 0.73 to 11, right? So down it's not saved. Then we are coming from here and 7312 and 7816. It's better than 7321. Then the module, it says value accuracy improved from this to this, saving model to this one, right? So like that, it checks the validation accuracy every time with the previous accuracy's best accuracy and save the model iteration. So in that case, always we will keep in track with this best model saving thing. Therefore, not the last. Early stopping is needed in order to avoid the overfitting and unnecessary GPU runtime, right? We'll stop whenever it's done. So those are the two other mechanisms that we use. Earlier, I have mentioned this accuracy-based testing saving model earlier also, but early stopping, this is the first time I'm telling. Yeah. So now we are teaching the model based on the audio. Okay, if yes is given to you, this is yes from one person voice. Like that, we have 1,000, 2,000 people voice recorded. Yes, 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 in different tone, different frequency, and everything. Now the good thing is, early days, we need to tell the model what is yes means, right? Because we need to say yes means this. Now, what we have done is the yes I do different way. Yes, you do different way. Your voice is different. My voice is different. My tone is different. So we have collected 2,000 sample and say this is yes. And we are telling the model now deep learning. That's the best of deep learning, right? These are yeses, right? I don't know how you identify. It's your problem. Identify. We give it through the convolution layer. It's identify error. Go on, back and forth. Do the training using these loss function calculation and the Adam optimizer. Try to find why certain features for yes, but we do not know what my model identify as yes and what your model identify as yes. I don't know. It's completely different. But somehow it identify as yes. If I give a word yes, it identify as yes. If I give a word no, it identify as no. So, but the features that I taken into consideration and you taken into consideration is the same because we are having the same convolution neural networks. But the weights are completely different, right? The features are the same, but the weights are different. So that's why your model accuracy varies from mine, my accuracy varies from yours. So it's completely random, right? So that's what we are going to see how our model is going to work, whether it's overfitted or not fitted, well not trained. So we can see. Still, the number of words are very less, right? So this is how the training. So there is very popular model available in the market. So you don't want to train these things from the scratch, which is already trained called Whisper, right? Whisper is a model trained using millions or billions of voices. Let me see that one. (2022), it's released by OpenAI and it has trained on, let's see how many. Sequence to sequence approaches, recurrent neural network, blah, thing, training capabilities. See, we have done 2,000 seconds or 20,000 seconds total data, right? The volume. Now they have trained on model on 680,000 hours. That means you can imagine how accurate it is, right? And 117 hours non-English data. 68,000, 680,000 hours means like we have to do the training. We can't do the training in Google Colab. So they have the Whisper already trained and it's open source available. So if you want to do some audio processing task, use the Whisper. Don't do the training because it's waste of time. So they have done 117 hours in certain English, Japanese, Mexican, Chinese, and certain languages, right? But you can see this 680 minus 117 are English. So that means English will be perfect, right? So now what we are doing the training, the whole data that we have using, including yes, no, and everything, coming around 20,000 seconds. Then you can calculate the hour, right? And out of that, we are taking only yes, no, up, down. So it will come around very less hours, like maybe couple of hours, right? So it's not enough. So anyway, this is the way to understand that we are doing. So finally, we have done the training for 100 epochs. And my final accuracy is around 0.9410. That is the training accuracy. How much you got? 93. So similarly, it will vary for everyone. That's fine. So now we will plot how is the loss function goes on. See, this is the issue. Now you can see my training is going down, but my validation is not going up. This is a symbol of overfitting, right? This is a symbol of overfitting. That means if both are going down after a certain scale, that means the training is happening, model is learning. Training is happening, model is learning. Now the training accuracy is going high. It's really good. But when you validated the train model, the accuracy is not improving. That means you are making the training in such a way to make the model going unfit, how to say this, overfitting, right? So in this scenario, if you enable the early stopping ES, it will stop before this happens. It will stop at this point, right? Then it will save that model as the best model. So now you will see the data. When you upload certain thing and listen, it's going to give a wrong answer. Most of the time, the same wrong answer because of the overfitting, right? We are going to listen that. That is also important. Now you can go and enable the stopping and do the training again in home. But now we are going to see what is going to happen. So I'm going to load the best model, which is saved over here while running, right? So that is the best model saved long ago. See, long ago. Because the validation accuracy did not improve after a certain time. So now, yeah, I'm going to create a function to record an audio and give it over here. Then prediction model. So I'm going to run. This is the truth predicting. Okay, I'm just randomly predicting from, okay, audio stop, text also predicted as stop. So let's say audio up, it's also predicted as up randomly. But let's see just the audio. So first of all, I want to record an audio. So record in my computer. I'm going to go to the sound recorder, right? Then I'm going to perform the audio. So I have already recorded yesterday. Hold on. I'm going to record again. Okay. Let me delete this one. Okay. Delete this one. Okay. Delete this one. Okay. Delete this one. Okay. So record. Yes. No. Left. Right. Okay. So I have recorded something. Let's see whether the machine is able to understand or not. So I'm going to go here, show in folder. I'm going to upload these all guys to my Google Colab, right? To this system. Okay. Now I have uploaded all the audios. You can also do it by in your computer. Let's try with mine, and you can write after I show you. Otherwise, everyone will say yes, yes, yes. Okay. So let's install certain thing to test the recorded video. So we have to do the BiDAP and FFmpeg. So these are audio processing because the file that I have recorded is M4A format. There are MP3 format, M4A format, WAV format. There are many other format. So, but I have trained the model in WAV format because all the audio file that I have in the data is .wav format, right? So first I need to do the processing conversion from .wav to another disk to net. So for that I need these libraries over here. So now I'm going to go here and put this maybe recording 2 copy path. I'm going to replace it over here. Okay. Okay. And I'm going to do the conversion to .wav file. So now the recording to M4A is converted into a M2 wave file. So in my file format, which I want to do the test. Cool. So after that, let's listen to the uploaded video, audio. Sorry. So this one, .wav, I need to copy path and I need to place it over here. No. So I said no, right? I said no. So now this no is another problem. This is in a higher sampling rate. This is in a higher sampling rate right now. So let's listen that sampling rate also, how much sample I have here. So it's around 4400, I believe, because all the things are here. So I need to down sample it. So first I need to resample that to 8000 because my size is 8000. If my sampling rate is input, the input shape is totally different. So I need to first change the audio and I'm down sampling it and I'm going to send it through my model, best model path. Model path is, we have defined it as this one, H5. So this is the recording video audio. I'm going to perform that thing, right? I'm going to put it here, replace it and see what my model detects. So in this thing, undersampling, and it's sent through the model and detects. So it's no, but it detected as yes. See, not good. Okay, shall we try the other one? So I'm going to do this one. I'll first go there and change the thing to WAV file first. Okay, then copy that WAV file here and place it in the one and we listen what is that one. Copy path and I will listen to that first by changing the path. I put left. So then again, I'm going to place it over here. Again, yes. What is the issue? Overfitting, right? Now you can see how a preach can overfit your brain by preaching these things. He can make sure and make you believe what he says. This is happening in all the religion, right? Right. So that's how our brain is overfitted with all the information, right? So the AI is overfitted now. So enable the early stopping in home, do the retraining, then do the model testing again, increase the number of epochs, do the model construction in a different way and see whether it works better or not. Okay. So now you know the concept, how it's trained. So now this is one word. How it's going to perform on series of words. Let's try that out. Okay. In the available. This is a speech to text model that we have embedded. This is not Whisper. This is not Whisper. Some other Google speech to text model, right? Okay, I'm going to talk now. What is the optimization function? Totally fine. It's good, right? Now I'm going to do the same question. What is the optimization function? It's getting it still, right? I can't speak faster than that to test you. If I speak faster than even this, it won't take certain words. Why? Because my voice is analyzed in millisecond gap. I'm talking continuously. What is the optimization function? It takes gaps, and send it through the model and predicting, right? If I speak two words in one gap they have defined, that moving window, it will not capture my word. You get it what I mean, right? I'm talking slowly. So the window size is millisecond, let's say. So it predicting the word, that is the input to the model. That is the input to the model, millisecond, maybe 500 millisecond, half a second, right? Half a second. So then that is the model input. So that moving window is, this is the time, my speech signal. Let's draw it, yeah. So this is the speech signal and speaking. So we create a window. This is called moving window. It's going to capture this point. And it's going to capture this point. Capture this point. There are overlaps. And these points. This point. And it's going to analyze this section only. So for this section, it creates the feature as we have created 8000. Send it to the input and predict. Send it to the input, predict. So what will happen? This is a small piece. If I speak certain words within this gap, 3 words, within this gap, 3 words, it won't be able to get. Right? Because maybe it can catch 1 word, but other 2 words it will not be able to catch. Right? So that's the issue. So let's try with another word. let's see some unborn words, right? Highborn. No, hold on. Let me try. Highborn. Highborn. It's not getting. See the issue, right? So that's how what they have done is they record our video, move the window, detect each and every paces, send it through the model, get the out, get the out. That is what happening in a very high speed, right? This is in gigahertz, right? Computers run in gigahertz. So we cannot speak in that high speed thing, right? So that's how they work. So now we have trained the model to do the one word detection at a time. So the same model, but there is a pre-processing in the real time. They move the window and the same model is performing and getting the output every time. Clear? Right now you know how the speech to text work, right? So that is the simple thing. So voice recognition is a complete different thing. We have done it using embeddings and the deep learning based also. But speech recognition, you should have deep learning. Otherwise, you can't do it, right? Or because earlier they have used some patterns to do that. But now, if you want to have the whole language to be detected using speech to text, then you should have. Otherwise, it won't understand. How say I say I go and it's a I believe or something, it was typed. It's completely wrong because it never heard that word in the training. Right? It tried to predict what it can be, the maximum percentage, right? So you know. So that's the issue. So today we have learned quite a good of stuff about the spectrogram, the audio signal processing, how it processed in AI. And we have learned about overfitting, right? That is very important thing in AI. So overfitting is very, very dangerous and it's not at all encouraging thing. So the early stopping in many applications is used to avoid overfitting. Okay. All right. So with that, we will conclude today's lecture. And think about how the text to voice is performed. Text to voice. We have done voice to text now. How the text to voice is performed. So let's discuss that in next week. So it's also not hard like this. It's a very simple techniques, but think about it. I will reveal that thing next week. So we'll go through that. So after that, what are the lessons coming up? Mm-hmm. 2, 3. We are in week 9 right now. So after that, this is text to speech, and this is natural language processing NLP. This is also under that sector, but we will do certain things. NLP means now other question. So in a chatbot, you ask a question, right? So it answers. So now it types certain words and it send it to the chatbot. So how the answers are coming back from the chatbot? So that is based on the NLP techniques that we are using, right? We will learn about that. So one more thing, you know that computer cannot understand words. AI cannot understand words. AI work with numbers, right? So how you ask a question in human language and it gives the answer in human language when we are working with numbers. So that's called the natural language processing techniques we have to use. Something called vectorization, right? Tokenization. So we are going to give numbers to each word, right? So that we'll discuss that thing over here. And dialogues with AI, that will be conducted by one of my student. So I'll be here, but he will do the lectures. So he's an expert working in a US company. Yeah, earning $4,500. He's just 27 years old. 4,500 per month he's earning just as an AI engineer, right? So it's better he's working on the same field. If he teach, he knows in and out more than me actually. Yeah. So, and the poster detection, that's a good thing. Weather forecasting and yeah, AI music and yeah, we are good to go. So more or less, we covered the basic up to this. By 10th week, any model comes in after here, you can sit and think and you can come with an idea. Okay, this is might be it is working. right? This is how it might work, right? You can come up with an idea. So when you say a new technique AI is telling, then you sit and think, okay, this is how this may be the way that they may have done it, right? That idea that you should have right now after learning these 9 classes. All right, with that, I will conclude today's lectures. Any questions? You have something to figure out, so we'll figure out. Okay. Until then, thank you. See you next week. Bye. So if anybody couldn't try it today, please go home and try it out. So this Kaggle is giving an issue.